Okay, well, good morning, everybody. I'd like to welcome everybody to the penultimate seminar in the fall 2024 Idaho Water Resources Research Institute and University of Idaho Water Resources 501 seminar series. Today, I'd like to introduce Neal Farmer, who's with the Idaho Department of Water Resources. And I'm going to just keep the intro pretty short. And Neal, if there's anything more you'd like to say about your background, please just jump in and add it. But otherwise, thanks again for presenting today, and I'll let you take it away.
Well, thank you for having me. It's been a couple of years since I've presented at this forum, and I've been with the department for 17 years, and since 2008, been directing groundwater dye traces on the East Snake Plain aquifer in the basalts down there. And so what I have for you is really a kind of a culmination of all of those years of data to show you, give you a flavor for dye tracing in these basalt systems, and mostly how they respond and how they behave, and some of the numerical characteristics that we've been able to generate. The tracing location is in southern Idaho, south central Idaho, where this star area is on the East Snake Plain aquifer. The aquifer is dominantly fractured basalts, and especially within the saturated zone of the aquifer, and so deeper areas can be rhyolites or maybe some sediments and stuff, but the upper levels of the aquifer are dominantly fractured basalt. The center image is the ESPA boundary, clipped out and modeled. We'll take a look at that later. And that's over an area of approximately 10,000 square miles. On the right is an aquifer recharge basin we call milepost 31 on the Milner-Gooding Canal. And we released dye, green fluorescein dye, into that recharge basin in 2016, and have some real nice results from that we'll present today. So zooming in, the red outline on the right is the ESPA modeled boundary, and the black lines, if you can see those, are groundwater contours. And you can see they're quite steep in some areas and flat in others. And most of our dye tracing has occurred and down in this area of this green dashed line. And most of the ESPA springs that discharge are on the west side of the ESPA. And the general groundwater flow is from northwest to southeast. Some of our first traces were in Malad Gorge at the Malad Gorge Springs in the upper left is Dave Blue with Idaho Power assisting the program. And then in the lower left at Niagara Springs is also Tom Ailey with Ozark Underground Labs. Tom has been dye tracing since I think it was the late 1960s, and he still continues to dye trace today and has a private lab with specialized equipment to analyze for different types of dyes. We invited Tom out to our our trace areas and asked him to evaluate our methods and procedures and techniques, and he spent a good part of 3-4 days out here in the field as well as in the office reviewing all of our practices, and then generated a report. And we came through with flying colors on that report for QA QC. Zooming in a little closer, if you're familiar with the towns of Jerome, Wendell, and Shoshone, are located up in here. Malad Gorge is located here. I assume you can see the cursor from the mouse. And we started our groundwater dye tracing at Malad Gorge in the a well that's the closest well to the springs, which is only 1,100 feet. Thus, since we started dye tracing, we've completed 25 traces at 13 locations, ranging from 1,100 feet, the first trace, up to 32 miles distance. Our general methods are for wells, we inject dye using polyethylene tubing over here on the left. And you can see the green dye being injected with polyethylene tubing. We don't just dump dye in the top of the well, because there'll be green dye in that well in perpetuity if you do that. On the right is releasing dye into milepost 31 aquifer recharge site. And that's in December 21st of 2016. And that's a 5-pound container this gentleman's holding. And the reason he's deploying that through a 4-inch PVC pipe is to help contain the powder so that it doesn't just blow everywhere. And we get that powder right to the water surface without it making a mess all over the place. We released 124 pounds of dye into the 75% concentration dye into this recharge site. There's a bunch more of those 5-pound containers sitting here down at the bottom. That site is located right here, and we track that dye through this large green area, as well as on down to Box Canyon. All these green areas are where we have traced. And so we'll look at down here by Mlad Gorge first, and how we did our tracing down in that area from wells to springs. Then we'll move back to aquifer recharge sites over here on the right at the Shoshone recharge site up here to the north, and then the milepost 31 recharge site. I'm going to skip the video today. So we test for dye typically always by sending our samples into the professional lab. They have highly specific equipment to analyze for dyes. And they have, of course, like half a century of experience doing this. Now, water samples give you instantaneous results at that location point in time, but we also use activated charcoal. It's a special type of charcoal, but it gives you an integrated result over the length of time that charcoal sampler is deployed, which means it is basically a sentry sampler. So if any dye passes through in between your grab water samples, your charcoal packets will pick that up and you won't miss it. We also use submersible fluorimeter instruments, and then calibrate those to lab grab water samples that we submit. Back in the early days when we didn't have any money for dye sampling, we used baby food jars and the elutant and charcoal, as you can see here. These are sample sites from different springs down in the Mlad Gorge, and you can see the concentration of dye from those springs being eluted out from those samples. So the three main methods for sampling actually change with time and space typically. So for example, this is just one example. Here's milepost 31 over here on the right, where we release dye in a recharge basin. And we would commonly use grab water samples and instruments in this zone. As you move further down the flow path, we switch to dominantly charcoal packets and grab water samples, although if I had to repeat that, I would place some instruments in this area also. But by the time you get to the distant lengths of the dye trace, you may only be using charcoal packets, which is dominantly what we did for the long distance sampling sites. So the green dots are where we have positive hits of dye, and the reds are where we had negative hits for this particular trace. And we had like 150 sample sites. So a little education. Pardon me, I had a cold last week, so I'm just getting over that. So clearing my throat. So this is a actual dye breakthrough curve from one of our traces, and it's a classic textbook shape, left skewed, single peak breakthrough curve. This is 10-minute data from an instrument, fluorimeter instrument deployed in a spring. And the first arrival of dye defines your maximum groundwater velocities. Your peak defines your dominant groundwater velocity. And then your average or mean is defined by the center of the mass. But so we'll talk about those throughout the rest of the presentation. So our stepped approach strategy started with the closest well to Malad Gorge in this red triangle area. So the well's a round circle in a park area, and it's 1,100 feet over to the springs in Malad Gorge. And all the springs we sampled are these little green circles down through here. And this is the spatial distribution of the emergence of that dye in a kind of a little triangle shape. Then we just looked at the next well back of the flow path, like this green one, and traced again there. And typically we trace twice at the same well just to reproduce the results. And then we moved, that was 1 mile distance in the green. And then we went back to about 2 miles here with the yellow, where it discharged in the springs, and then back to the pink and its spatial distribution of dye emergence in the springs. And then this black line that's dashed, if you can see that, down in the springs here. Then we moved lateral to this kind of orange left side and also the blue side. So it was a very effective methodology. And what it did is it taught us how fast the dye is moving through, how many sample points do we need to capture the information from the dye emergence, and how long does it take for that cloud, dye cloud, to pass through the system. And so every trace was a teaching or assisted us with planning the next trace. These are groundwater velocities for some of those traces, maximum velocities on top and dominant velocity underneath. I don't know if you can see that, but our first trace, we had 5,800 feet per day units, groundwater velocity, and that was the maximum. The dominant velocity based on the peak was close to 2,000 feet per day. And you can see this one's 2,400 and 839. Yellow is 2,950. Pink is 1,530. And the 3¼ mile trace back here, black, is 564 and 212. And obviously you can see a progressively slower velocity, and this is an integrated velocity over the length of the trace as the distances increase, and the groundwater gradient flattens as you get away from the springs and steepens towards the springs. This is a sample of breakthrough curves from instrument data from a number of different traces. A short trace about 0.4 miles to the south at Clear Springs rather than Malad Gorge, showing a classic left skewed single peak breakthrough curve. We did, I think, 3 traces at that particular location. So our first one was a very weak trace, and so we basically started doubling the amount of dye. By our third trace, we were up to nice, healthy breakthrough curve concentrations in the green. The second down is 0.7 mile trace, a nice single peak breakthrough curve, classic textbook there. Then another left skewed with a possible second peak, which would be a second flow path in this particular trace. Down on this one, then we have some more centered and right skewed traces, response in the breakthrough curves. This is a 2¼ mile trace in the upper right, and the lower right is a 3-mile trace with a real nice single peak center skewed breakthrough curve. Just some examples of those patterns of the breakthrough curves. So on the right chart over here for Malad Gorge, we did the first trace on a 3.1 mile distance from the Victor well. And that was the yellow column of data results. And you may not be able to see, but there's some zeros in here, these springs here. And then we got some hits here. We didn't sample here. We got a hit here and here, and we didn't sample that one, but we sampled these. And so we had this little more sporadic sampling across the Malad Gorge, and that distance is 1 mile from left to right. But we learned how fast the dye came through and where it came through, which springs. So the second trace in red, you can see we hammered all those springs and have a real nice normally distributed bell-shaped curve dye concentrations from those springs in the Malad Gorge. And we also increased the amount of dye because we saw that this is very weak response in yellow versus the red. On the left is the same thing, but I think we used the same amount of dye, if I recall. As you can see from trace 1 and trace 2, red to green, they're almost identical results, along with zeros lateral. This is over a ½ mile distance left to right, and a nice normal shaped breakthrough curve response horizontally in the springs. Now we move away from the spring areas to the east to our aquifer recharge basins. And the first one we'll look at real quick is up near Shoshone, the town of Shoshone. We have a recharge basin where we turn water out of the canal from a structure here located up by this building and flood the basalts out in this area and let the water course seep into the ground. And we did 2 traces at this location, and this is the green fluorescein dye in those basins. And by the way, our reports for nearly all of these traces are on our website under the technical documents. So you'll find the Shoshone trace report at the Managed Aquifer Recharge site located there. These are breakthrough curves from the Shoshone recharge basin tracer tests. Tracer test number 1 is in red. And those are grab water samples, the red squares, and grab water samples in the blue symbols. The instrument data, 10-minute data, is green. And we did 2 traces there with, I think, the exact same amount of dye, had a slightly different concentration, but the shape and timing of that breakthrough curve were essentially the same. And this is at a 3-mile distance, 3.1 mile distance away from the recharge basin. And it's approximately 200 feet from land surface down to the water table in this area. Then this inset graph is just showing how we would stop collecting our instrument data because it's gone to 0 essentially. And then we continue to collect post-seeding grab water samples just to kind of monitor anything that might come through later on. Milepost 31 recharge site. Again, this is green dye being deployed in December, and the basin is mostly froze over, flowing out into the basin there. We have some of our field instruments that we use to pump water out of monitor wells, dedicated monitor wells near the basin, and record that data from grab water samples as well as instrument data. And part of our QA/QC is to compare and contrast data sets between different field instruments. And also in case one field instrument fails for some reason, we'll have another instrument collecting that data. So the Milepost 31 recharge site is located east of the town of Jerome. This is the town of Jerome here by about 15 miles out in the desert along the Milner-Gooding Canal, where we turn water out of the canal into a closed basin or aquifer recharge. And these are breakthrough curves from different locations down that dye flow path. And near the basin, we have instruments that recorded peak concentration of about 16 parts per billion, but drops dramatically as that dye moves away from the basin very quickly. In fact, the first arrival of dye in a well that's 250 feet horizontal and 250 feet down to the water table after we released dye just took 24 hours for dye to reach that well. And so that's basically through the Vado zone of 250 feet of basalts. All these red dots are sample locations, and this dashed line is areas that we detected dye in those wells. This is a 8-mile distance, 8 to 8.5 range right here, transect, our first main transect in between the recharge basin and this location. There really aren't any wells. It's all desert area with no wells. But these are some examples of the breakthrough curves from those wells in that transect with groundwater velocities, maximum velocity versus dominant velocity in the range of 500 feet per day and 400 feet per day. It only took 2 months for dye to travel from the recharge basin 8.5 miles to a number of these mostly domestic wells that we were sampling. These breakthrough curves and this distribution of the dye cloud was a snapshot at 6 months into the trace. And so we actually detected dye in water samples out at 19 miles over here on the left edge. And at the 15-mile distance at this location, the fluorescein dye was detected in water samples, not charcoal, at 0.01 parts per billion. And so it's extremely low concentration of dye. Most of these others at the 8-mile distance are running about 0.2 parts per billion. And so that's pretty typical of our concentrations. They're very low. In fact, you never see the dye in our groundwater sampling locations. Of course, you do see it where we release the dye, but it dilutes so fast that by the time it travels some distance down the flow path, you don't see it. It can only be detected with highly sophisticated instruments. So this is that 8-mile distance transect called the Prescott transect. And those are all the breakthrough curves plotted against each other. As you can see, they're all single peak. And these are grabbed water samples, not instrument data. And their peaks and timing and shapes are all very similar. This is over a distance of about 2.5 miles roughly from south to north, about where this dashed arrow is. And what this graph is showing on the lower right is that the wells to the south received the dye sooner in time. And this is a projected interpolated value here based on an incomplete breakthrough curve. But regardless, the lower these data points are on the graph means the sooner in time that the dye arrived, which is the south. And then as you travel north along that transect, the dye arrived in the peak. This is the peak concentrations, later and later time. And so we'll see how that plays out in some other information. So now we're looking at about an 8-mile transect from south to north. And these are the peak concentrations of these wells along those that transect from zeros in the south till we start to get some slight breakthrough concentrations here, and then it peaks out and comes back to the north, back to zero. And as these yellow data points are out of alignment, and so how we dealt with that is modeled all this data in here, and then used the modeled data to bring them back into alignment. And then that modeled data for just those 3 data points is plotted on the right. And as you can see, from north to south, this lateral dispersion of dye is very homogeneous with a nearly normal bell-shaped breakthrough curve from north to south. Even without the modeling, it still has that trend in there. This is a 3D view of all of, not just the cross section at 8-mile distance, which is located about right here, but all of our water concentrations of dye out to 19 miles, which is located here. This is the town of Jerome, and this is the town of Wendell. North is up and to your left. So the recharge basin is back to the east here. And the dye cloud is moving through longitudinally in a very bell-shaped curve. And then again, a modeled cross section at the 8-mile distance shows a very nice bell-shaped curve in that dye concentration. And then this is just located or draped on top of a land surface DEM. And so at this location, we're halfway the distance to the springs at 6 months after we released dye at 19 miles. And ultimately it landed down in Box Canyon. And again, we had over 150 sample sites to trace, to sample for this trace. Another view of that is from the east rather than from the west. And this time, the land surface DEM is amplified in a 3D view rather than the chemical data of the dye. And the recharge site's located here, and that dye flowed westward down to this location. As you can see, it deflected around the north side of this large feature here, which is a shield volcano called Flat Top Butte or Jerome Butte. And there's some evidence, geologic evidence from one well is drilled straight down the top of that butte that very dense basalts are located above the water table and below the water table at that location, which may be causing a low K environment, very dense environment, according to the driller's description, and deflecting that dye off to the north around that shield volcano. And so, so this is view Box Canyon's out here to the west where the dye eventually landed. And so it does kind of make sense with the peak timing of the peak breakthrough curves for all these wells for just a 2.5 mile distance, which is just right across the heart of the dye cloud. That it has a more southwesterly flow, reaches the south area, and then deflects around to the north in the timing. The Snake River Canyon is over here to the left, just to show you that. And then these are all our sample sites. We have some vertical data of that 8-mile distant transect, Prescott transect of 7.5 mile distance from south to north, left to right. And just as an example, this is kind of draft right now. I've just been working on, and the green is where we detected dye. The blue is where we didn't detect dye. These are wells and open intervals of the well versus the saturated thickness, or from the water table down to the bottom of the well. For example, this one, there's 120 feet of water in that well, but the open interval doesn't open until 75 feet down below the water table because it's cased and sealed. And so those samples from that breakthrough curve are sampling at this depth of 75 to 120 feet below the water table. Conversely, this well here its open interval, which is these little horizontal lines, is open to the top portion of the aquifer, and then a variety of in-betweens all across here. And so all of these had very similar breakthrough curves, as you saw earlier, regardless of whether they were withdrawing water from 100 feet down or, let's say 25 feet down below the water table in that area. This particular well is an irrigation well right here in the center with a blue column where we didn't detect dye. And the reason I think we didn't detect dye is we had really poor sampling conditions there. We kept losing our packets. They would disappear. We don't know why. And we also had poor flow conditions in that particular well. This is another irrigation well that's deep over here where we had excellent flow conditions for the packet to reside in. And this one here, we just didn't have any access or ports to get good sampling there in a lot of times. And then we kept losing our packets and we don't know why. So dye could have actually arrived here, but we just missed it because of incomplete sampling. Then modeling comes into play back in the aquifer recharge site, milepost 31. The USGS actually performed aquifer pumping tests in a well just a couple miles west of the recharge site. And they determined a conductivity of 9,300 feet per day from their aquifer pumping test. That's published in Lindholm, 1996. And then using our groundwater trace data and this equation from Lohman and Vetter with this information to punch into the equation, our groundwater trace data says that hydraulic conductivity is 9,277, nearly identical to the USGS test. And then we used hand tush modeling, analytical modeling using MoundSolve software version 4 with these inputs for that to match the peak groundwater levels at the recharge basin. And so if you can focus on the solid yellow line and the solid blue line, those are two different monitor wells at the recharge basin. And during a recharge event, and the recharge event is the red line. And so the basin fills and then drains out. And then these are the responses to that. And so using that input to match the peak water level reached in the groundwater system at near the basin, recharge basin in two of those wells is the symbol data with dashed lines, symbol yellow, symbol blue. And those two modeling exercises generated the same value of 9,300 feet per day as the USGS. So all three of these are in very close numbers and are in alignment. And so it's been nice to see the dye tracing come up with similar results as both these other sources of data. So now we have kind of a combination of all the data sets together, not just the recharge sites and not just the spring areas. And so this is a look at the longitudinal dispersion of fluorescein dye, which is the dye of our choice. And so on the left, you'll see very short, high amplitude peaks of breakthrough curves for dye, and those are short traces. As you can see, those are half a mile and 0.7 miles, 1 mile, etc. Then as you get longer distance traces, those longitudinal dispersions start expanding and extending outward until our longest trace at the 8-mile distance, which is the black line located here from the milepost 31 trace the recharge site. So that's a little snapshot there of the longitudinal dispersion. And so we also have some information about lateral spread in these basalt aquifer traces versus the distance. And so these are our lateral dispersion traces. These are short distance traces and longer distance traces here. Our mile+31 trace is way out here by itself, but we had really excellent data for the lateral dispersion. So it's a really high quality data point, even though it's isolated from the other traces. And an exponential trend line shows an R² value of 0.95 correlation between lateral spread and the distance of the trace. Then if we look at the dominant velocity versus the distance of the trace, we have a really nice R² value of 0.9 using a power trend. These are short distance traces over here, and this is high velocities and lower velocities through the curved section of the trend, extending on out to 32-mile distance at Box Springs. And again, this is the distance versus dominant velocity of the breakthrough curve. The inset chart is just truncated to only the 8-mile distance for NP31, but actually improves the R² by including it down to the Box Canyon area for 32-mile distance. Now, the maximum groundwater tracer velocity versus groundwater gradient, we just applied a linear trend for an R² of 0.93. And then the dominant velocity versus groundwater gradient is shown here, which I think is much better data set with an R² of 0.90. And these are the long distance traces here. So because they have a lower velocity, and then our short trace high velocities in the upper right, and the groundwater gradient for those traces. So if you accept that those relationships are valid, and that the velocity is proportional to gradient, then it conforms to Darcy's law according to Meinzer with the USGS, and that's the source of that information. So now if you know the gradient at the ESPA, and you can plug that into the equation for that relationship, then you can plot up the groundwater velocities of 10,000 square miles of basalt aquifer. Of course, there's an assumption that it has the same characteristics of fractured basalts down in the lower ESPA as fractured basalts through the rest of the ESPA. My visual observations through well videos and other information is it's very, very similar in nature, but it is an assumption to extrapolate that data from the west end or lower part of the ESPA to the rest of the ESPA. But given that, these do seem to show where you have tight contours in here, up in this area, higher velocities, and tight contours around the spring areas of the discharge of the ESPA, showing extremely high velocities, you know, on the order of 3,000, 5,000 feet per day of groundwater velocities. And conversely, where there are flat contours, you have very low velocities on the order of, you know, maybe 100 feet per day in these ranges. And this modeling exercise does correlate to our, comparing to our actual field data, does come out very close in the data that we get from the field data measurements versus the modeled data measurement. So this is a plot. This is what everybody asks when they want to do a dye trace. How much dye do we use? And for this type of aquifer, basalt aquifer, fractured basalt, the actual amount of dye we used for the distance of the trace is shown in these green symbol line at the lower part. But upon further just evaluation and reflecting back on our response patterns, in my opinion, every one of these traces, with the exception of this one, we should have had twice as much dye than what we released. We had a weak signal to noise ratio in my opinion, of all those traces. And they should have been a lot more dye released. But you can roughly use a distance squared times 3.5 from a distance for ranges between 1 and 8 miles to get you in the ballpark of how much dye to use. I wouldn't bother with trying any mathematical equations to try and calculate how much water's down there and how much dye, and then what's your concentration goal that you're trying to reach, because it probably won't work. And that's some opinion of some other professional tracers also. The cost is about $55 a pound. Again, we released 124 pounds at the milepost 31 trace. Lab analyses are about $55 a sample. That may have these costs may have changed recently, but it's in this realm. And field fluorimeters, pardon me, cost approximately $3,000. And so, yeah. Okay. Any questions? That's dye tracing since 2008 or 9 in a nutshell on the ESPA.
All right, well, thanks, Neal. We can take questions from the group. Feel free to just jump in with a hand up or verbally or drop something in the chat. Yeah, I'll ask one question that had me that I thought was sort of interesting, was looking at some of those dye trace trends, the breakthrough curves. And so this gets a little bit more kind of the general question is, I was thinking you had one curve in particular that kind of had a shoulder on it that you mentioned, you maybe have 2 different flow paths. And so just kind of curious more generally, what can the shape of those breakthrough curves potentially tell us about geology?
Right, and so they are essentially a function of the dispersion characteristics along that full flow path. That's it in a nutshell. And if you have multi-peak responses, then you'll get potentially a multi-path response. But dominantly, we have not had multi-peak responses in a fracture flow system, which is kind of stands in contrast to what most people assume happens in these aquifer systems. So our heavy hitter is the milepost 31, where we have single peak breakthrough curves from numerous locations at great distances, and with some pretty good vertical information along with those. And we're not even getting multi-peak responses in a massive trace that's 8 miles long and 6.5 miles wide in the dye cloud. And even the trace up at Shoshone recharge site, there's maybe the slightest evidence of a possible second flow path down here in this area. But I mean, if you just look at this flow path, the breakthrough curve, it's just classic left skewed single peak breakthrough curves that we see dominantly throughout the plain in our tracing. But overall, it's a function of the dispersion characteristics of that particular location in those fractured basalts.
All right, thanks. And there's, I don't know if you can see the chat, there's 3 that just came in. I'll just start with the first one, which is, how long did it take for the milepost 31 trace to reach Box Canyon?
Approximately 2 years. So it reached, that's for detection. So let's take a look at that, because I think that's a very good question. In fact, I'd really like to know who asked that. But let's see here. So it's a very good question. if you'll notice, this is halfway to Box Canyon where we detected dye at 19 miles, and it's only 32 to Box. So this is a 6-month post dye release time snapshot. So if you use this travel velocity, you land in Box Canyon in another 6 months. So that's 1 year for the first arrival of dye. The caveat is, can you detect it? Because one, we didn't design the trace to, we actually only designed this trace to track where dye landed 8 miles distance, the first transect of wells. But we had such excellent results coming through that we actually just chased it. And so we established additional north-south transects along the flow path. That's why this one's a lot shorter, because we were getting short on resources to establish these real long north-south flow paths. And so by 32 miles, yes, the first arrival of dye may have occurred really at approximately 1 year for a maximum groundwater velocity. But can you detect it? And so we actually had such probably low concentration of dye and low amounts released, even at 124 pounds, that if we wanted higher confidence results in our first arrival, especially, we should have had twice as much dye. In fact, we've talked about reproducing or redoing this trace with about 300 pounds of dye instead of 124. But the concept is that these are extremely low concentrations of dye. And so by the time you're located 32 miles away, you're reliant on charcoal packets. And charcoal packets kind of function like a piggy bank, where maybe you drop a penny in every day. And at the end of 6 months, typically we were sampling these about every 6 months. You would send the packet in or crack open your piggy bank and see how many pennies are in there. But if you don't have enough dye molecules or pennies in that sampler, the detection equipment at the lab cannot detect it, even though the dye is actually present. And so what we learned in that trace, and we only did one of these, is that we started deploying a packet, 2 packets in these areas, and we would collect a 6-month packet, and then we'd leave another packet in there for a year. And we did find out that there were times where we had no detection of dye on a 6-month packet, but we had detection of dye on a 1-year packet. And so it gets a little bit tricky when you have really dilute concentrations versus a hard hit. Now, our solid detections of dye in Box Canyon were likely due to the peak of this break cloud passing through. So there was enough dye molecules given our sampling methodology that we were able to detect the peak, but the first arrival was probably too dilute for us to detect. So the peak traveled through at about 2.5 years, 2 to 2.5 years, which makes sense. But the maximum or leading edge of that dye cloud likely made it there literally within a year.
All right, thanks.
Mm-hmm.
There's a bunch of
very good question.
There's a bunch of other good ones coming into the chat as well. The second I'll just jump to says relationship about velocity to gradient. Steep gradients typically reflect low hydraulic conductivity, not high hydraulic conductivity. Velocity should be directly proportional. Did I misunderstand your assertion that high velocity occurs with high gradient?
Yep, the assertion is high velocities with high gradient. That's correct. Mm-hmm.
And then there's another one here that says, is there a reference that you can share that summarizes research and results?
Could you repeat that?
Yeah, it was just a question of whether there's a reference that you can share that summarizes the research and results.
So most of these are in reports on our website, if that means anything. And this particular, the milepost 31 trace report is in progress. So the Shoshone trace reports on our website, and then all the traces down around the springs are on our website. And then this information was also presented at the groundwater conference also 2 years ago. So there's a source for that. That would be on the first slide.
Great. And then we've got a student that's actually working on a groundwater flow velocity meter. So I'll just read hers, and that is there any other instrumentation to measure the groundwater velocity like groundwater heat pulse flow meters, or does fractured basalt make other instrumentation difficult?
Well, we've looked at actually temperature data because a lot of our aquifer recharge occurs in the wintertime. And as you saw in those photos, the temperature of that water in the basin is 32 degrees. At least, you'd think it'd be frozen at 32, but it'll actually be still liquid and flowing at 32. So that's a really cold water signal from the recharge basin down through the aquifer system. And we've been trying to use that temperature data to help us track and understand how it's been behaving. We haven't used any physical instruments to measure groundwater flow, but we have done a lot of well videos to measure a groundwater flow. Now, I didn't include one video, which I was going to, because I thought maybe we'd be short on time, but we do have one where we, at Box Canyon, many years ago, we placed a camera at the bottom of the well looking upward and a camera at the water table looking downward, and then discharge dye at the water table. And there was a strong downward gradient in that well and flow to where we track that dye from the water table down to the lower camera, which I think was 32 feet or something. And you can, calculate it just a time distance on the amount of water flowing velocity vertically in that well. And that's in the groundwater discharge areas where there are steep gradients, so near the spring areas.
And Neal, if you have time for a couple more, there's some more that came through in the chat.
Yeah, that's fine.
All right.
Give it my shot.
Okay, here's another one. Says, how can dye tracer tests be used to facilitate estimate of time for quantities of recharge to arrive at points of diversion? Relationship is probably not one-to-one.
The point of diversion, I'm not sure what that means, but I'm a little unclear on what the goal of the question is. I guess what they're trying to do is try to track how much recharge based on dye tracing, but I'm not sure that we've ever looked at any of that information. So we might have indirect information associated with that topic, but I don't think we've ever looked at that specifically.
Then I'll jump to the second to the last year, which is, I may have missed this, but did the time of year of the tracer dye injection affect the measured velocities?
No, not really. We haven't seen any of that so far. And that's one reason why we've done multiple traces we've tried to do at least 2 traces in the same well or same location. And we haven't seen much difference in the difference between our traces. You can see the breakthrough curves are very similar. Essentially, the gradient is pretty much the same, even though there might be a a rise or lowering in the water table from one year to the next year, but the gradient typically stays the same. So I haven't observed anything that's significant in that particular factor that's involved with this.
Okay. And then I'm going to just jump around here a little bit. There is a request for you to go back to the first slide, just for grabbing some background information. And then while you're doing that, I'll just fire off another question, which came in here from Mac, which is, how can the results be used to help with the Eastern Snake Plain Aquifer management decisions? For example, do the results influence future groundwater recharge efforts?
Well, one of the useful tools out of groundwater tracing from aquifer recharge sites is that it has informed us where the water flows in the subsurface and delineates that in relative to where our monitor wells are. So at milepost 31, we have a monitor well that's west of the site about a mile, and it received essentially a very, very small amount of dye very late in time. And conversely, a couple other wells that are located nearby had immediate and strong response. And so based on the lack of dye response or detection in that particular well, along with other information like water quality sampling data, as well as temperature data, we were able to basically remove that well from our sampling, water quality sampling regime. And so to try and optimize our efforts in the field and then focus our sampling where we know the water is flowing from the aquifer recharge site. That's been a pretty useful tool in terms of water quality. And also, this is some of the first really tangible and empirical data on the ESPA, especially for, if you didn't catch it, but vertical flow through these basalts. So we've got numerous tests now vertically across horizontal basalt flows where, you know, some of the traditional views are that those horizontal basalt flows can retard water flow vertically, but at the Shoshone site, milepost 31 site, W Canal site, which is another recharge basin, we've got dye moving vertically from land surface down 200, 250 feet, very fast. You know, MP31, it's in 24 hours. It's reached the water table. So.
Well, we're just about out of time. But Neal, I want to say thanks again, and really interesting work. Really appreciate this.
Yeah, you're welcome. It is
Great.
interesting.
Yeah, hope to meet you in person one of these days.
Sounds good.
All right. Cheers.
Okay. Bye-bye.
Bye.